There's a term in our chemistry books called active metals. We point out on the periodic table some metals that are active. Lithium, sodium, potassium. Zinc is an active metal. Magnesium is an active metal, calcium. And what does it mean when we say it's an active metal? And that's something, that you want to really show your students to give them a sense of what's happening with it. The other part of it is you also want to show how the periodic table and periodicity relates to active metals and metals that we sometimes call less active, or in some cases even noble metals like silver, gold, platinum. And magnesium's a great one to work with. I use magnesium all the time in my chemistry class. It's just so simple to work with. I mean, magnesium and hydrochloric acid, I can use it to illustrate 100 different things. Burn a piece of magnesium in the classroom, lights up, it's bright, every kid in the room gets excited by it. Just really simple to work with, easy to do, and a lot of your students have done it at one point or another, and oh yeah, let's burn some magnesium. That's fun. But to look at how active the stuff really is, we need to take a look at some more reactions. We're going to look at, first of all, the very simplest one, and that's just the fact that magnesium reacts with water. And so I'm going to put a small amount of water in a test tube, and I'm going to pour into that test tube a small quantity of magnesium turnings and just let them fall down into the bottom. So I'll do that. Get these guys to slide down. These that are floating on top, I'm set on the bottom. Already we've seen something really kind of interesting. Magnesium is more dense than water. It's sunk to the bottom. We also see a little surface tension phenomena because I've got one piece that's sitting on top still. So we'll push that one down too to get it at the bottom. That in itself is kind of cool. Now I'm going to heat this. Strange flame. Better flame. Right here is something that you want to kind of keep in mind as far as safety is concerned. Test tube tilted a little bit on an angle. Probably don't want it straight up and down. I always tell my students, don't point the test tube when you're heating it with a liquid in it at your lab partner. Don't point it at yourself. That's really stupid. If you put it vertically, it'll shoot up and get everybody. It's kind of an umbrella effect. And when you heat a test tube with a liquid in it from the bottom, you don't stick the Bunsen burner underneath it and incinerate the stuff, but you start out by gently heating it to give it a chance to warm up. And I think you can probably already see this, and this is kind of cool. See those bubbles? Now I'm going to do something now I don't ordinarily recommend a lot, but I'm going to touch the side of the test tube. This really isn't all that hot. It's just a little bit warm. That's not boiling water. That's the magnesium reacting with the water and generating some hydrogen gas. Now, I've tried collecting the hydrogen gas that's being generated here, and I've had very little luck with it. Every once in a while I'll be able to get enough that I can get into a test tube and give me a nice popping sound. But it's an iffy process at best. And so I'm not going to even try to do that here. But instead I'm just going to look at another part of the reaction. When magnesium reacts with water, hydroxide ion is one of the products, along with the hydrogen gas. And if hydroxide ion is being generated in there, then I ought to be able to see that if I put an acid-base indicator in there. And I should see that I have a basic solution here. So I'm just going to drop in a little bit of phenolphthalein. And if I've let this thing react long enough, let me turn the Bunsen burner off here first. If I've let this thing react long enough, I should get some pink color. So let's hope that we get it. Ah, there it is. Do you see that right when it falls in? See the pink? Hydroxide ions are in there. All right, so I didn't collect the hydrogen because that's a little bit difficult to do sometimes, but I can certainly see that hydroxide ion has been produced, and so the reaction is taking place. So I'm going to go over the board real quick and write the reaction just so you have an idea what's going on. It's magnesium solid with water. And if I were right-handed, it would have worked. Liquid generates hydrogen gas and magnesium ions. This is, you ever seen that sign that says plan ahead? Well, I'm doing that really well here. And hydroxide ion. And I can balance this a number of different ways. My personal favorite thing is to use fractions because it takes less effort on my part. And I think that's not balanced. Yeah, that's balanced. And so this is the reaction that's going on. Again, you can try collecting the hydrogen gas, but it's not a really easy thing to do. It just doesn't generate enough. Visualize a magnesium fire in a factory somewhere where they have large quantities of magnesium. Fire department arrives. They start putting out the fire in the typical way, which would be with a hose and water. The water hits the hot magnesium. What's generated? Hydrogen gas. Boom, the whole place blows up. I have talked to people that work in fire departments and asked them, what do you guys do when there's a magnesium fire? And most of them say, we get out of the way, back up, try to protect the buildings around it, and let it burn itself out. Because it's really just almost impossible to put out a magnesium fire once it's going well. And there are some ways you can do it, but the things that you have to put on the fire aren't easy to deal with. I mean, you could dump sodium chloride on top of it, and that would be fine. You could dump magnesium oxide on it, and that'd be great. But you know, there's not a lot of magnesium oxide lying around. I know in San Francisco, they told us that their plan was if they had a magnesium fire on the first floor of a building, they would bring in salt trucks and a conveyor belt and run salt up to the second floor of the building, fill up the second floor with salt, and then when the fire burned out the supports on the first floor, the second floor would fall down on top of it and put the fire out. I thought that was kind of a neat idea, but in essence, the building's destroyed, so I'm not quite sure what the point is beyond just, you control the fire a little bit better. So here's our first example. An active metal, a metal that reacts with water, one that's pretty common that we see all the time. Magnesium is used in alloys and all sorts of different things, and yet it's active enough to be able to take out of that H2O to pull the oxygen away from the hydrogen and generate a hydrogen gas. So that's kind of a neat reaction. Now we're going to take a look at another reaction of magnesium that to me is even more bizarre and is really kind of cool chemistry. So I'm going to go back to the periodic chart for a second, and I want to take a look at that. And I want to think about what's going on there. Carbon dioxide, CO2, silicon dioxide, SiO2. Carbon dioxide we know is a gas produced in combustion products. We also know that carbon dioxide is used in fire extinguishers. Carbon dioxide will react with magnesium. Magnesium is capable of pulling the oxygen away from carbon dioxide and burning, and in fact, burning very well in carbon dioxide. If you go to any Boy Scout, etc., and say to them, hey, how do you put out a fire? Smother it with sand. Sand is silicon dioxide. Now, Mendeleev is rolling over in his grave laughing right now. Because if magnesium is active enough as a metal to take oxygen away from carbon dioxide, magnesium will probably be able to take oxygen away from silicon dioxide. And again, I'm going to go over to the board briefly, and I want to think about that reaction first. And so here I'm talking about SiO2, magnesium, And my products this time are going to be silicon and magnesium oxide, MgO. So let's take a look at this reaction and see whether or not it actually happens. And because it's kind of fun to work with. I guess just to be good, I'll balance the thing. All right, so let's go back. So now I'm going to take some sand, silicon dioxide, as you can see, sand, dump it in. This is really nice sea sand. I mean, this is great stuff. It's clean and granules are all the same size. There aren't any little rocks in it or dead fish or anything. One thing that's important with this, make sure it's dry sand. The reality is when I first started doing this demonstration, I just went out and grabbed some sand out of a sand pile in the backyard. Wet sand is a bit of a problem. And sand with a bunch of junk in it is a bit of a problem. And you'll see why once we run the reactions. But you know, try to use a little bit purer stuff. It just has a real advantage. And I'm going to take some powdered magnesium just to give me a little more surface area and speed the reaction up. And mix that in very carefully. Yeah, a little more. You can measure it, but it doesn't really make a whole lot of difference. And I'm going to just kind of shake this around so that I get kind of a nice mixture of magnesium and sand together. And I'm going to place that in a test tube. This time, you want to use a heavy wall Pyrex test tube. What we used to call an ignition test tube. Not sure that they still sell them as ignition test tubes, but get a heavy wall Pyrex test tube. If you use some of those culture tubes that you find for sale, the thin glass ones, in a very short period of time, you'll see why that's not a good thing to do. So I'm going to slide that in. Let's see. I want to line this up so that the back is best for the camera here. That pretty good for you guys right there? Okay. I'll bring it back up to that position after I dump the solid in it. Okay, so let me get this thing in here. And the amount is not all that critical. Get some in. When you get it in there, you want to shake it out so that it's flat, so you've got a lot more surface area on top. So that should do the trick. And now I'm going to heat this vigorously for a little while. It's going to take a bit of time for this thing to really get going. We might want to dim the lights a little bit here. This is the point where you may hear, after I've heated it for just a short period of time, a very, very slight pop. There's always a little bit of moisture in the air. When I start heating this stuff up, some of that moisture is on the surface of the magnesium, and a little hydrogen gas gets generated, and it'll ignite. So you'll hear like a poop, and that'll be just the first bit of it. And what I've done there is I've gotten rid of the moisture that was inside the test tube. After that, I've got a situation here where there's not a lot of oxygen inside the test tube. The magnesium that's in there will react with the oxygen in the test tube, and I'll get magnesium oxide. After the oxygen's been used up, the magnesium's going to start looking for something else to react with. And the only other choice in there is the sand. And actually, there's a third choice, and we'll see that too. But in fact, you can see the moisture collecting on the side, although that's really just from the combustion of the butane from this particular burner. So I'm going to heat this. This does take a little bit of time because I've got to get it really hot. And then once I get it good and hot, the reaction will take off. And it's kind of cool. So why don't we dim the lights to kind of dusk here. This is some of the coolest chemistry around. The first time I did this and watched what was happening, I was so excited. I ran around and grabbed every chemistry teacher at the school I was at, said, "You gotta come and see this." I think I did the reaction like 7 times. You gotta see this, this is so neat. I would have never thought sand and magnesium would react with each other. Now we're getting there. We may or may not get a little pop here. Donut doesn't always pop. Ah, there it is. How cool. And you can see some of the little sparking right now on the edge of the test tube. That little bit of sparking is the magnesium reacting mostly with the oxygen that's trapped inside the test tube. We also used up some of that oxygen that was in there when the hydrogen. All right, see again, you can see right at the surface of the sand right now, just a little bit of glowing. Shortly here, I think I'm going to get to the point where this reaction is going to start to take off. Yeah, there we go. You can maybe just hear a little bit of it. Get back into this. Second. Now remember something here. This is a heavy-walled Pyrex test tube. And I don't know if the camera can get here, and I'm not sticking my finger under this part, but if you look right down here along the bottom, that smooth glass that was there, it's now glowing red hot. This reaction has a delta H, a heat of reaction that's larger than the heat of reaction for magnesium burning in the air, in oxygen. There's more energy given off there. And so the test tube has changed. And also, you can maybe just pick out the fact that the shape of the test tube has started to change. I've actually done this. Actually, the first time I did it, I didn't do it in a hard glass test tube, and the bottom of the test tube just melted right out. Stuff just fell out on the tabletop. I'm going to finish this reaction off so I've got the whole thing. I didn't heat the back of it quite enough, so we'll finish this up real fast. There it goes. So we've got the whole thing. You will also find, and we're not going to do that right now, but you will also, see, look at that glow. That sucker is hot. You will also find that this test tube has micro cracks in it at this point. You're not going to be able to use it again. The other thing I want you to take a look at, and what I'm going to do is I'm going to play a Julia Child here. And when we come back and it's cooled off, here's what we have. And you can look at this test tube, and again, now I think you can really see on this one, same kind of test tube, how it's changed. You can see almost the modeling there on the inside, the bubbles. And you see this cool silverish glow on there, or silver color? Look at that and go, what the heck is that? Well, I said there were 3 things in there for it to react with. You know, the oxygen, the sand, but what's the test tube made out of? You know, glass is mostly silicon dioxide. So it's reacted with the test tube itself. And I've got silicon metal, or silicon metalloid, I guess, or semi-metal, whichever word your textbook uses. I've got silicon formed on the outside of the test tube all around it. Some of you probably do the lab where you take magnesium and put it in a crucible and burn it to make magnesium oxide. It's probably the most common formation of a compound stoichiometry kind of lab that we do in chemistry. And when you get done with the lab, you've got these crucibles that have this black coating on the inside of it. And I know when I first started teaching, I used to, you gotta get that cleaned out, kids. Come on, get it out of there. 15 years later, first time I did this reaction and started thinking about what was going on, I think, that black coating that doesn't come out of there, what the heck is that? It's silicon. Because there's a glaze, a silicon glaze on the inside of the crucible. And in fact, you get a better, not that it really matters because the percentage is minuscule, but actually a dirty test tube, one with silicon on the inside, is a better one to use than a brand new one because there's a little reaction going on there that you aren't accounting for. in your lab write-up. So that's really amazing. So anyhow, this is kind of neat. And you can, again, you can feel this, you can see it's cracked. This test tube is useless at this point in time. There's nothing you can do with this later on. Now, that's cool. And that's some great chemistry. And it says to me, hey, look, stoichiometry and periodicity are so cool. Carbon dioxide reacts with magnesium. Magnesium is an active metal. It can take oxygen away from carbon dioxide. It can take oxygen away from silicon dioxide. If I could find some germanium dioxide, it would do it. And in fact, I've looked it up in books and it says it will. I've never had any, I've never tried it, so I don't know. But in theory, it should work its way all the way down that table. That's just great. I mean, this is what Mendeleev did. This is why we believe in the periodic table. And that's kind of neat. But what's even neater was that after I did this the first time, I started reading some more and found out there's one more thing you can do with this. I'm going to go back over the board just briefly to point something out. This reaction that I wrote here happens inside that test tube. But we know, as science teachers and people who spend a little time thinking about burning and those kinds of things, when we write on the board, methane reacts with oxygen to make water and carbon dioxide. It says in the book that's complete combustion. In the real world, that like never happens. If you burn something, you get all kinds of junk getting kicked out besides just carbon dioxide and water vapor. I remember going to the National Bureau of Standards in Washington, and they've got a section there where guys do my dream job. They burn stuff. They actually like build hotel rooms and set them on fire to see what happens and how the fire goes, and it's just such a cool job. But there was one guy there that we talked to that had spent years studying all of the products that are produced when you turn a Bunsen burner on and burn it in a classroom. You know, how many different things. And he'd identified, I don't know, 60 or 70, I've forgotten the number now, 60 or 70 products that were produced from burning methane in a Bunsen burner. And it's just, that's amazing. In this one, it turns out there's some side reactions. And one of the side reactions is really neat. You know, once the magnesium can't find any more oxygen from the sand, it starts looking for something else to react with. Well, what else is in there? Well, I made some silicon. So the magnesium reacts with silicon. And so I get magnesium plus silicon, and it makes a compound called magnesium silicide, which is Mg2Si. And so in here, I've got silicon, I've got magnesium oxide, and I've got a little magnesium silicide. Now, I can't see that, but I was reading somewhere, and it said that if you react magnesium silicide with hydrochloric acid, it makes silane. Now, I knew what silane was because I'd read about it. It's SiH4. It's the silicon analog of methane, CH4. And I'd read a lot about silicon compounds, in particular in science fiction stories, because the science fiction story would be the silicon-based race comes to Earth, you know, and the silicon monsters come out and they eat Tokyo or Peoria or someplace, and it's kind of cool. And they're all shiny and they look like silicon and they march around and they're a little stiff. And so hey, wouldn't it be neat to make some silicon, some SiH4, a silane compound, and see what happens? And so I did what it said when I was reading. I tried taking some, and I got a little in here, I think. I'm going to pour that out, product out, into this dish. just like Julia does. There it is. Isn't that wonderful? Oh, this is going to be good. I'll mash it up a little bit. It's kind of lumpy, but it should be all right. And I'm going to dump some 3 molar hydrochloric acid in here. And maybe a pipette too. Hey, this is just like in my classroom. I don't own a bottle that doesn't have a pipette inside it. All right, set that aside. Got it here. Again, we want to dim the lights a little bit on this one. Let me ask the guys, we're going to need a side shot here because we're going to see some bubbles when I drop this stuff in that are going to be formed when the product goes inside there. But we're also going to want to see it from the top later as the silane is generated. So are we in a good spot for that now? Okay. All right, so I'm going to drop this in. We'll go to the dusk setting and we'll see what happens here. Oh yeah, listen. Oh, cool. Some's good, more is better. The bubbles that are being produced in there are silane. They're rising to the surface and they're hitting the air. The SiH4, when it hits the air, spontaneously combusts. And so it catches on fire. And so you see that, you can hear the popping noise and you can see the little flashes as the silane spontaneously combusts in the air. You can also see, if you guys are looking at this thing down from the top, that there's some grayish looking stuff that's in there floating on the top, really fine crystals. If you burn silane, SiH4, in the air, what are your products going to be? Well, water, H2O. What's the other one? It's not going to be CO2. If it was methane, it would be carbon dioxide. So in this case, it's going to be SiO2. And SiO2 is sand. And so we've come back and regenerated the sand. Just so neat. So again, you go back to the periodic table and you go, methane, CH4, burns in the atmosphere. But it doesn't burn without a kick. You got to give it a spark to get it started. Activation energy is fairly high. The next silicon analog of methane, SiH4, its activation energy is lower. And so silicon, it's still popping a little bit, you can maybe hear it. SiH4, activation energy is low enough so that at room temperature, SiH4 spontaneously combusts in the atmosphere. Now, every good demonstration, and this is a great one because talk about wonderful periodicity. You know, we've looked at magnesium and it's how it reacts with silicon and with carbon dioxide and with water and those kinds of things. And we've got the methane and the silane thing. But a good story always goes well with this. So I started thinking about this and I started going back to my science fiction and thinking, okay, so the silicon-based monsters come to Earth. Or beings, they don't have to be monsters. The silicon-based beings come to Earth. They walk out of their spaceship. What happens to them? Not a good situation, especially if they land, oh, say in Miami, where it's fairly warm. Going to be a significant problem for them. In addition to that, now I start really thinking about this, and there's some pretty amazing possible implications here. Things that I've always wondered about. You know, one of my favorite scientific journals, The Weekly World, periodically has an article about spontaneous human combustion. And they'll talk about, you know, some person incinerating as they're walking down the street. It occurs to me that maybe that's not impossible, that a silicon-based life form has come to Earth. they've put on a suit over top of their silicon body that protects them, just like a spacesuit does, from the oxygen in the atmosphere. And as things may happen, occasionally there's a break. If the suit breaks open, what happens? We just saw it. Poof! What we need to do is go check out that ash pile. Because if that ash pile is, you're right, wet sand, then in fact, that has been a silicon-based being that has spontaneously combusted when his spacesuit has broken open. So I thought about this some more. And some things started to occur to me that have to be true, or at least could be true. Back during the last ice age, in fact, a large number of silicon-based beings came and set up colonies on the glaciers. And as the climate changed, it got warmer and the glaciers receded, of course, each colony spontaneously combusted and left behind water and wet sand. I contend that in Minnesota alone, there were 10,000 of these colonies, and that the remains of them are still there. And so I thought about this some more. And I started thinking about early archaic Indian lessons that were handed down verbally over time. And you know how things, as they get handed down over time, have a tendency to get mixed up or changed. And I believe that the early American Indians saw this happening. And they watched these communities spontaneously combust, one right after the other. And as they saw it happen, they said, wow, death is a beach. And when the American settlers came in, and of course they mixed up the two terms, they switched it over to, and I'm sure you know the answer to that. This is truly a cool demonstration. It's a cool series of reactions. It's something you need to do because the chemistry is just so elegant and so much fun. The story, that's up to you. But the rest of it is just so much fun and so neat. And there's so many things you can do with it, and it has so many great applications that it is, for me, my favorite demonstration of all the ones I've done in 30-some years of teaching. Thank you.